My name is Ioan Sarbu, and I am a Professor Emeritus and Doctoral Supervisor at the Department of Civil and Building Services Engineering at the Polytechnic University of Timisoara, Romania. I obtained a diploma in civil engineering in 1975 and a PhD in 1993. Additionally, I am a European engineer, as I was designated by the European Federation of National Engineering Associations Brussels in 2001. I became an assistant professor in 1978 and ultimately dedicated nearly 50 years to teaching and research since 2004. I have been a PhD supervisor in the field of civil engineering and building services, supervising up to 20 PhD students, 50 master's theses, and over 200 graduates. I was head of the Building Services Engineering Department within the Polytechnic University for almost 20 years. Until my retirement in 2017, between 2001 and 2017, I was also head of the first-degree National Building Equipment Laboratory in Timisoara. In 2019, I was named Professor Emeritus and became a laureate of the Henry Coanda Award of the Romanian Academy for 2017. In 2023, I won the Best Paper Award from ScienceFather, India, at the 7th International Research Excellence Awards. I serve on the editorial boards of several journals, including Energies, the Science Bulletin of Polytechnic University, and the Romanian Journal of Civil Engineering. As an editorial board member, guest editor, or academic editor and reviewer for more than 20 high-impact journals. I served as the coordinator or participant on almost 100 grants and research projects. I have published about 400 scientific papers, 41 books and 10 book chapters in prestigious publishers in the country and abroad, over 150 articles in journals indexed by Clarivate Web of Science and other international databases, and about 60 articles in international conference proceedings. I am also the author of 6 patent certificates, 15 innovations, and more than 30 computer programs. I received multiple international lifetime achievement honors and recognition among the top 0.5% of researchers worldwide per the 2025 Scholarks rankings. Numerous fundamental and advanced theoretical, experimental, and numerical studies were conducted. They have published in different journals and have made significant contributions to advances in building services engineering, which can be grouped into the following categories. 1. Energy optimization of buildings that simultaneously achieve energy savings, increase comfort, and ensure normal air quality in rooms. 2. Energy analysis, modeling and optimization of district heating systems and low-temperature heat distribution systems in buildings. 3. Improving the energy performance of refrigeration and air conditioning systems, focusing on vapor compression-based systems with ecological refrigerants and implementation of an air-water mist-cooled system for the air-cooled chillers of different vac systems. For utilization of renewable energies such as solar heating and cooling systems and geothermal heat pumps. 5. Analysis of thermal energy storage technologies focused on latent heat storage systems associated with phase change materials for use in solar heating and cooling of buildings, solar water heating, and heat pump systems. 6. Hydraulic simulation and optimization of water transmission and distribution systems, including the development of new, high-performance models for hydraulic analysis of loop distribution networks using variational formulations. Original models for optimizing design and choosing their optimal route using deterministic methods, as well as proposing solutions to optimize the energy efficiency of these systems. 7. Improving the energy efficiency of pumping in a water or heat distribution system in variable speed pumps and proposing a formula to calculate the efficiency of a variable speed pump when its operating point is altered. 8. Designing local sewage treatment plants for small localities and developing a generalized model for hydraulic calculation of complex open channels and vertical sewer columns in buildings. 9. Numerical modeling, simulation, and application of computerized calculation, using both classical and modern numerical methods with finite and boundary elements implemented in original computer programs, as well as the commercial software Turnsies for trenchant system simulation. Most of these issues were addressed in the reference book Advances in Building Services Engineering, published in 2021 by the prestigious Springer Publishing House. To hasten the decarbonization of buildings by 2050, it is imperative to deploy highly energy-efficient technologies, such as the electrification of the thermal sector through heat pumps HPS and the integration of renewable energy sources RACE. The most widely applied race is solar energy, with photovoltaic PV cells commonly installed on roofs and walls to convert solar radiation into electricity. Solar thermal collectors are also employed to provide hot water and space heating. Geothermal energy, generated and stored within the Earth's crust, is independent of climatic conditions such as solar radiation or prevailing wind. For the first time, the European Renewable Energy Directive 2009/28/BC recognizes energy from air, geothermal, and hydrothermal sources as a source of renewable energy, opening up a significant chance to utilize HPS with a seasonal performance factor of SPF greater than 1.15 WTA, where ETA is the efficiency of power generation from primary energy. Overall, the integration of diverse race, including solar, wind, geothermal, and hydropower, provides nearly zero energy buildings with complementary and reliable options to balance energy supply and demand throughout the year. In the current context, where the construction sector is responsible for about 40% of final energy consumption and nearly 36% of total CO emissions in the European Union, a thorough understanding of the performance, limitations, and potential for integrating these systems into the built environment is essential. Thus, the research experimentally investigating and numerically simulating the performances of various low-temperature hydronic heating, cooling systems connected to a vertical closed-loop ground-coupled heat pump, published by Energy and Buildings in 2023, is focused on the energy efficiency explorations of various low and very low-temperature hydronic radiant heating, cooling systems floor, wall, ceiling, combined floor-ceiling, and of the medium-temperature radiator heating system, connected to a vertical ground-coupled heat pump GCHP in W-tube borehole heat exchanger bay configuration. The main performance parameters are obtained for 5 weeks of operation in heating mode and 3 weeks in cooling mode, and a comparative analysis of these parameters together with indoor thermal comfort is carried out. The four simple heating systems radiator, floor, wall, ceiling have relatively small differences, maximum 7.4% in their coefficient of performance COP values, but the number of stops in the case of radiator heating is twice that of floor heating, which leads to greater wear and tear on the heat pump equipment. Under the same operating conditions, the CO2 emission of the radiator heating system are 0.716% higher than those of the heating system with radiant panels floor, wall, and ceiling. The floor-ceiling combined radiant heating system has the highest COPSIST of 5.45 as well as the lowest CO2 emission value of 2.15 kilograms. The predicted mean vote PMV index per 1.1 met 0.29 kilo has values approximately equal to 0 only in the case of the floor-ceiling heating, when the percent of likely dissatisfied with the thermal comfort is 5%. The three cooling radiant systems show differences in their energy performance, namely the radiant ceiling cooling system has the best COPSIST, 39.8% higher than that of the radiant floor, and only 5.9% higher than that of the radiant wall. The values of the PMV index per 1 met 0.9 kilo for the radiant wall cooling system are 31 to 41% lower than those of the radiant floor and 10.4 to 14.2% lower than those of the radiant ceiling. Finally, numerical simulations of the useful thermal energy and the system COP and heating and cooling modes are performed with Turnsey's software for a duration of 8,760 hours and then analyzed and compared with the experimental tests to validate the simulation models. The paper investigation by monitoring and numerical simulation of the performance of a ground source heat pump system with and without regeneration in different configurations and operating modes, published by Applied Thermal Engineering in 2024, is focused on restoring the thermal imbalance of the ground caused by conventional ground-coupled heat pump GCHP systems through seasonal and continuous regeneration using a geothermal solar facility, with a vertical GCHP combined with PV and PV thermal PV-AT panels in a heating-dominated climate. Located in Timisoara, Romania, therefore, the performance of a GCHP system integrated into the heat supply system of an experimental office, operating in single and W2BHE configurations with regeneration in the summer months by injecting heat into the ground, is experimentally evaluated. Exploratory research has indicated an increase in the average temperature of the working fluid, by 2.4% and an improvement in system performance when using heat injection seasonal performance factor SPF by 3.5% and 6.6% higher, and CO2 emission by 1.2% and 3.8% lower in the single and W2BHE configurations, respectively. Additionally, numerical simulations with Polytechnic software are used to test the performance of the hybrid GCHP-PV-AT system with continuous PV-AT panel regeneration throughout the year, and of a conventional GCHP integrated into the heating and DHW production systems for a single-family building. The simulations were experimentally validated through measurements on the geothermal solar facility for heating and domestic hot water DHW production in the experimental office. The simulation results show that the SPF values of the hybrid GCHP-PV-AT system in the single and W2BHE configurations, 6.00 and 5.79, respectively, are 32% and 34% higher than those of the conventional GCHP system for 0.56 and for 0.32, respectively. In addition, the SPF in the single U2BHE configuration is 3.6% higher than in the W2BHE configuration for the GCHP combined with the PV-AT array 31.8 square meters. The study thermal protection impact assessment of a residential house on the energy efficiency of the air source heat pump radiant floor heating system, published by Thermal Science and Engineering Progress in 2025, investigates, through both in situ measurements and numerical simulations, the thermal protection impact of a residential house located in Timisoara, Romania, on the effectiveness of the floor heating system interconnected to an air source heat pump ASHP into test cases, 1 conventional ASHP and 2 hybrid ASHP with PV collectors. The performance of the heating facility supplied by the conventional ASHP is evaluated through in situ monitoring in heating mode for the house envelope, both without thermal protection and with 15 cm thick expanded polystyrene EPS insulation. COPASH and COPSIS values of 3.59 and 3.3 were obtained for the solution with a non-thermally insulated envelope, and 3.92 and 3.53 for the solution with an EPS insulated envelope, higher by 8.4% and 5.4%, respectively. Also, the CO2 emissions for the second solution were 42.3% lower than those for the first solution. Additionally, the main performance parameters of the heating system supplied by the ASHP combined with a PV array, 7.8 square meters, are investigated through numerical simulation using Polytechnic software, both in heating and DHW mode. For the building without thermal insulation, and with 15 cm thick insulation from different materials, such as EPS, extruded polystyrene XPS, mineral wool megawatt, and polyurethane per. The per insulation yields the best seasonal performance factor SPF for the hybrid ASHP PV plant, both in the heating regime, 6.95, and in heating and DHW mode 5.54, closely followed by the MW insulation. In heating and DHW mode, the SPF of 4.70, corresponding to the non-insulated building, is 15.2% smaller than the SPF of 5.54. Corresponding to the 4 insulations, and 35.5% higher than the SPSIST of the conventional ASHP system, which is equal to 3.03. Finally, a comparative economic analysis of the two heating systems reveals a superior capital cost for the ASHP PV system, but a financial advantage in operating expenses, enabling the recovery of additional investment within an acceptable 6.5-year period. The novelty of this study does not necessarily lie in a shorter investment recovery period than that of simple insulation, but in an integrated analysis that combines in situ monitoring data with numerical simulations using Polytechnic, which provides a robust approach for validating the results. However, future research should focus on quantifying the impact of freezing ice formation on the evaporator on the seasonal SPF of ASHPS at low temperatures, which involves monitoring defrost cycles, quantifying the energy consumed specifically for defrosting, and analyzing the impact on SPF and sensitivity to freezing conditions, relative humidity, and outdoor air temperature. The study exhaustive overview of advances in integrating renewable energy sources into district heating systems, published by Sustainable Cities and Society in 2024, offers a comprehensive review of the recent advances in various aspects of district heating systems DHSS. focusing on the fourth and fifth generations of heat distribution networks integrated with different race. The review highlights the integrated approach of various advanced renewable technologies applied to DHSS, such as solar and geothermal energy, biomass, industrial waste heat, and especially the implementation of conventional heat pumps HPS and solar-assisted HPS with solar thermal PV or PVAT panels in resilient and sustainable buildings and DHSS to increase energy and environmental performances. The ineffectiveness of refrigerant can be used to evaluate quickly the HP energy efficiency only with the values of the operating temperatures and to evaluate the energy performance of the HP PVAT hybrid system. The use of the global seasonal performance factor is also considered. Additionally, it shows the possibility of recovering excessive pressure from DHSS using pumps working as turbines. The study also describes the major components and evolution of DHSS, briefly reviews low and ultra-low temperature DHSS and implementation of borehole and hot water TES technology into DHS. It also discusses the main optimization techniques, simulation tools, control methods, and maintenance for DHSS, as well as alternative connection modes of race to DHS. Different methods of modeling district heating DH networks exist. The most widely used is the coupling of the node method with the Newton-Raphson algorithm. Meta-heuristic optimization methods for DH networks, such as genetic algorithms, simulated annealing, and colony optimization, and particle swarm optimization, have attracted greater interest recently. These techniques solely utilize objective function values to find the optimum, resulting in significant computation time. Finally, some original research and a literature review are included on several applications of implementing various race and resilient and sustainable buildings and DHS as part of smart cities' intelligent, sustainable energy systems. The development of district heating calls for more adaptable energy systems that must include building automation, race, and greater prosumer involvement. Further investigation is required to identify the specific challenges in monitoring, operating, and maintaining the 4GDH and 5GDH networks, enabling proactive maintenance techniques to be successfully applied. Another work from the last 3 years entitled Optimization of Urban Water Distribution Networks Using Heuristic Methods, an overview, published by Water International in 2023, provides an exhaustive overview of the most commonly used heuristic optimization techniques for water distribution networks WDNS, focusing on their optimal design. A single and multi-objective optimization problem is formulated, and the main optimization objectives, decision variables, and constraints for the design, rehabilitation, and operation of WDNS are synthesized and discussed. Additionally, the primary heuristic methods are briefly described and classified. Finally, the literature on heuristic optimization models for WDNS is reviewed, and the advantages and disadvantages of the heuristic techniques used for WDN design are discussed, along with recommendations for future research directions. This extensive study makes the following contributions: a comprehensive collection of studies in the WDN area using optimization methods, evaluation of the performance of some of the most widely used heuristic algorithms, identification of the main shortcomings in the literature, and the proposal of additional studies to develop this research field. Further research on heuristic techniques should focus on hybrid methods that combine the specific advantages of different approaches, although they are difficult to program and implement. These studies should also use hyperheuristic methods for optimizing WDNS, which are more general and can solve a broader range of problems than current metaheuristic methods specialized in a narrow class of issues. All these studies, published in indexed Clarivate journals, support the dissemination of Romanian research results worldwide and the advancement of knowledge. Thank you for listening.